Welcome to tutorial 20 in the Practical RF Design tutorial series. My name is Dr. Prakash Sangaran and I am a Keysight certified expert. In this tutorial, we will learn the complete design and optimization guide for a novel multiband planar inverted L antenna. This antenna is implemented on a rigid printed circuit board. This antenna covers 617 MHz to 960 MHz, 1.71 GHz to 2.2 GHz and 2.3 GHz to 2.69 GHz. This antenna supports technologies such as 4G or LTE, 5G, Wi-Fi, Bluetooth, Zigbee, amateur radio 900 MHz and 2.3 GHz, UHF frequencies, LoRaWAN, Sigfox, RFID, TETRA radios, and satellite bands such as L band and S band. This is a 4-part tutorial. In tutorial 19, we will cover antenna introduction. In tutorial 20, we will cover antenna selection, design and optimization part 1. In tutorial 21, we will cover antenna optimization part 2. In the last tutorial, tutorial 22, we will cover antenna optimization part 3, antenna EM simulation and results analysis. Let's continue with tutorial 20. Let's move on to our first step of antenna design, which is antenna selection. What antenna we are designing? There are many antennas to choose from as shown in the table below. There are dipole antenna, loop antenna, helical antenna, Yagi-Uda antenna, spiral antenna, corner reflector antenna, parabolic reflector antenna, patch antenna, PIFA antenna, bow tie antenna, log periodic antenna, slot antenna, cavity backed slot antenna, inverted F antenna, slotted waveguide antenna, horn antenna, Vivaldi antenna, telescope antenna, fractal antenna, monopole antenna and NFC antenna. The question is, how do we select an antenna for your application? To choose an antenna for your application, you need to ask this question. Specification of the antenna, physical dimension or size of the product or antenna, radiation pattern requirement, whether it needs to be directional or omnidirectional radiation pattern. Is there any polarization requirement, secular, linear, elliptical? For example, military and defense satellite communication application have secular polarization requirement for the antenna. Antenna implementation, is it implemented on a PCB or ceramic chip? This figure here shows antenna specification. This specification is chosen for our design, so we have to design an antenna that meets all the specification. Let's go through the specification one by one. The frequency of operation is 0.61 GHz to 0.96 GHz, 0.17 GHz to 2.2 GHz and 2.3 GHz to 2.69 GHz. The return loss must be less than -6 dB. The antenna radiation efficiency must be more than 75% and the maximum physical dimension of the antenna must be 45 mm by 105 mm. Previously, PIFA antenna design was done in the tutorials 15, 16, 17 and 18. To meet the specification given in the table 5.3, we selected an inverted L antenna. An inverted L antenna is nothing but a bent monopole antenna. Since the antenna is implemented on a PCB, it's called Planar Inverted L Antenna. Let's move on to our second step, which is antenna design. Before we design the antenna, we need to understand how the antenna works. Before we study the inverted L antenna, we will study the monopole antenna first. A monopole antenna is one half of a dipole antenna always mounted above some sort of ground plane. The case of a monopole antenna of length L mounted above an infinite ground plane as shown in figure 5.5a. Using image theory, the field above the ground plane can be found by using the equivalent source in free space as shown in figure 5.5b. This is simply a dipole antenna of twice the length. The fields above the ground plane in the figure 5.5a are identical to the fields in the figure 5.5b. The monopole antenna fields below the ground plane in the figure 5.5a are 0. The radiation pattern of monopole antennas above a ground plane is also known from the dipole results. The only change to note is that the impedance of a monopole antenna is 1/2 of that of a dipole antenna. For a quarter wavelength monopole, the impedance is half of that of a half-wave dipole, so the Zin is 36.5 plus J21.25. This can be understood since only half of the voltage is required to drive a monopole antenna to the same current as dipole antenna. Think of a dipole antenna as having plus V/2 and minus V/2 applied to its ends, whereas a monopole antenna only needs to apply plus V/2 between monopole antenna and the ground to drive the same current. Since Zin equals to V/I, the impedance of a monopole antenna is halved. The directivity of a monopole antenna is directly related to that of a dipole antenna. If the directivity of a dipole antenna of length 2L has directivity of D1 in decibels, then the directivity of a monopole antenna of length L will have directivity of D1 plus 3 in decibel. That is, the directivity of a monopole antenna is twice the directivity of a dipole antenna of twice the length. The reason for that is simply no radiation occurs below the ground plane, hence the antenna is effectively twice as directive. Monopole antennas are half the size of their dipole counterpart and hence are attractive when smaller antenna is needed. Antennas on older cell phones were typically monopole antennas with an infinite ground plane approximated by the casing of the phone. Figure 5.6 shows inverted L antenna. An inverted L antenna is nothing but a 90-degree bent monopole antenna. The horizontal element has a quarter wavelength spacing. The vertical element is a fraction of the wavelength. Inverted L antenna has low impedance. A regular planar inverted L antenna is a single band antenna. Moreover, a quarter wavelength at our lowest frequency 617 MHz is 121 mm. In order to make planar inverted L antenna radiate at multiple band at shortest resonance length, we need a novel antenna. We have learned that current carrying wire radiates when it's curved, bent, discontinuous, terminated or truncated. We will put this theory to test by creating a novel miniaturized antenna that radiates at multiple band frequencies. Let's move on to our step 3 of the antenna design, which is antenna optimization. We will design, build and optimize a novel inverted L antenna for this tutorial to meet all our design specifications. In ADS, layout optimization is called parametric EM simulation. There are two ways to do a parametric EM simulation in Keysight ADS. The first method is to create a schematic using TETRA-microstrip palette components, followed by creating the layout from the schematic. The second method is creating the layout in the ADS layout straight away. We will use the first method for this tutorial. The first step of creating and optimizing an antenna using method 1 is to draw the antenna shape you want to design in the ADS schematic using components from the TETRA-microstrip component palette. A new schematic needs to be launched to build the antenna. In order to launch a new schematic, you can click the icon shown here and click on Create Schematic. The next step is to navigate to TETRA-microstrip component palette. There are many component palettes can be found here. The component palette that we are interested in is TETRA-microstrip. As you can see, there are many types of microstrip lines available. It will help us to create the unique antenna shape design. For this tutorial, I am just going to use the antenna that I have already created. I am not creating an antenna from scratch because many optimization have already been done to arrive at this shape. It will take a long time if I show every optimization. This is the antenna schematic we created for the optimization. To design this antenna shape, we use mlin, mt_ads, mgap MC-FIL and MCON. Let's look at them one by one. MLIN is a basic microstrip line which is a straight line with width and length. MT_ADS is a microstrip T-junction. MGAP is a microstrip gap. MC-FIL is a microstrip coupled line filter section. MCON is 90 degrees microstrip band. After placing microstrip components, we connect them together using wire. With this, tutorial 20 comes to an end. For inquiries, please email pragash@innovave.co or visit www.innovave.co.